Okay, now we will discuss about the rutting prediction models or the rutting transfer functions. Now, what is rutting? It is the deformation that you see along the wheel path in the transverse direction. So, this is a distress that we observe in the pavement surface, which could happen due to many reasons, and we need to predict this rutting so that so that you can design the pavement structure without this rutting being exceeded beyond a particular value. Now, when I say rutting, as I said, this is the deformation that you see on the top pavement surface. Now, there are two ways in which this rutting is considered, or two ways in which this rutting is modeled. The first one is that you will consider the vertical compressive strain on top of the subgrade alone, which is called as a subgrade rutting. So, the assumption is that you see a rutting on the top of the subgrade. So, this is a subgrade layer, and this rutting get transferred, and you see that as a rutting on the top of the pavement surface. Okay, so this is called as a subgrade rutting. Essentially, the rutting in all other pavement layers is not considered when you talk about the subgrade rutting. Whereas the second approach is that you find out what is the permanent deformation or the rutting that it happens in every layer of the pavement structure, and then that is accumulated to see what is the total accumulated rutting on the top surface. So, when I say rutting, it is essentially what you see on the surface of the pavement, or when I say the permanent deformation, it is the deformations that happens in each one of the layers. Okay. Now, as in the case of fatigue damage, here also there has been certain rutting models. A general form of rutting model that has been developed, Asphalt Institute and Shell, considering the subgrade rutting. Okay, so for subgrade rutting, the expression is given as ND is equal to F4 epsilon C raised to minus F5. Now, what is this ND? ND is the number of repetitions of failure due to rutting on this pavement surface, whereas epsilon C represents the critical vertical or the maximum vertical strain on the top of the subgrade. So, this is the critical strain that is considered in this rutting transfer function. Now, various studies have tried to correlate the pavement surface rutting with this epsilon C, that is the critical strain that we observe on the top of the subgrade while doing a layered elastic analysis, and then the factors F4 and F5 has been estimated. So, as you can see here, Asphalt Institute has given the factors of F4 as 1.3 into 10 raised to minus 9 and F5 as 4.477, and the failure criteria that has adopted is for a rut depth of 0.5 inch, whereas Shell has given these parameters at various reliability levels of 50%, 85%, 95% and so on. And then UK RRL, TRRL has given at 85% reliability level, and for a rut depth of 0.4 as a failure, the parameters or the coefficients F4 and F5 are given, and also you can see some values for the by the Belgium Road Research Center. So, you see that these parameters, the F4 values as well as F5 values varies from the varies among the various agencies, but mostly the changes is more in the case of F4 as compared to F5. Now, let us see how this rutting is considered in IRC 37 2018. So, in IRC also you consider the subgrade rutting as the rutting criteria. So, the failure condition that is considered is an average rut depth of 20 mm along the wheel path. Okay. Now, the distress transfer functions are given correlating the equivalent number of 80 kN standard load repetitions that can be served by the pavement before a critical rutting failure of 20 mm occurs. Now, as I said, it is given for two reliability levels in IRC 37. One is NR is for 80% reliability level, and the second one is for 90% reliability level. NR is given as a coefficient as 1 by epsilon V raised to 4.5337, and for 90% it is 1.41 into 10 raised to minus 8 into 1 by epsilon V, whereas epsilon V denotes the it's similar to that epsilon C that was written earlier. It is a vertical compressive strain at the top of the subgrade which can be obtained by the layered elastic analysis of the pavement structure. Okay, and NR here represents the subgrade rutting life, or the cumulative equivalent number of 80 kilonewton standard axle loads that can be served by the pavement before this 20 mm rutting is happened. Okay, rutting happens. Now, what we have discussed is the rutting expression as far as the subgrade rutting is concerned. So, essentially all other layers are not considered in that equation. You see what is the strains that happens on top of the subgrade, and it is related to the pavement surface rutting. Now, there are not many distress functions which are directly commonly used for rutting of HMA and other granular materials. But essentially the approach that is adopted is a rutting rate concept that is used that can be used for HMA, granular, and as well as fine grained soils, or the various layers of the pavement structure. So, this is generally represented as a permanent strain that is happening in the pavement material or any type of material, which is given as an expression epsilon P is equal to A n raised to B. So, this was adopted in the NCHRP National Cooperative Highway Research Project, and this expression is derived from a experimental study of a material and from the log epsilon P log n data, where n is the number of load repetitions. Okay. So, this expression actually represents what is a permanent strain that is accumulated in a material when loaded with n cycles. Now, the Ohio State model, there has been many models which are developed as in line with this expression. So, I will discuss about this Ohio State model, which essentially assumes a linear relationship between this permanent strain epsilon P and the number of load repetitions in a log scale. So, you can see a similar a picture drawn here which shows the relationship between epsilon P by n. See, rather than taking the permanent strain epsilon P, the rate of permanent strain, which is epsilon P by n, is noted here, and n is the number of load repetitions, and the plots are made for different stress levels and at different temperatures. You can see that the stress application of 29.76 psi, then application of 40 psi and so on, and also at different temperature levels. See, till here the temperature is 1000 Fahrenheit, this is 100 degree Fahrenheit, and beyond that this is like 120 and so on. So, a series of experiments are conducted on materials at different temperature levels, and the accumulated permanent strains are captured, and then it is plotted here. So, and then from this, so a linear relation can be developed, and the rutting rate is indicated as epsilon P by n is equal to A n raised to minus m, where A and m are the constants, which essentially depends upon what is the material type and what is the state of stress which is used for testing the material. Now, this relation can be, if you have to write it in terms of epsilon P, so that becomes epsilon P is equal to A n raised to 1 minus m. Now, many other studies have been conducted to arrive at or see how these constants of A and m varies. So, Kaiser has conducted a large number of repeated load tests on HMA specimens, and they found that they've tried to find out what is this A parameter, the parameter A, with the modulus of the material or the strain in the, or the elastic strain of the material. So, as you can see here, there is a plot being made with MR by sigma D. So, MR actually represents the resilient modulus of the material, and sigma D represents the applied stress. So, you do a repeated test on the repeated loading test on the specimen having a modulus of MR and with a stress level of deviator stress level of sigma D, and MR by D essentially represents the elastic strain. Okay, the elastic strain versus this parameter A from this expression shows that there is a linear variation. So, A itself can be written in terms of small a into epsilon raised to B, okay, where the small a and b are the material constants. So, you have conducted a number of tests on various bituminous mixes, and to find out these experimental constants of small a and b, or to get this relation between uh, the parameter a and the elastic strain of the material. Now, substituting this in the epsilon p equation, you can see that the final form of the Ohio state model becomes epsilon p is equal to a epsilon raised to b into n raised to 1 minus m. As I said, m is the experimental constant which depends upon the material type. A and B are again material constant, and epsilon is essentially mr by sigma d, which is the resilient modulus by the applied stress, or it is the elastic strain of the material, and epsilon p represents the permanent strain. Okay, so what is interesting here is that your permanent strain that happens in the material is represented as a function of the elastic strain in the material, or the recoverable strain in the material. Now, how we can predict the rut depth of different layers of a pavement structure? Suppose you have different layers, and for each of these layers, you can divide it into a number of sub layers if you want, and for each of these layers, you can do a stress analysis and see what is the stresses and strains at different heights of each layer. Now, for convenience, you will consider the mid layer of each of these layers, and you see what is the radial stresses as well as the vertical stresses that happens at the mid layer of these pavement structure, and then use that stress conditions, that is, you have the normal stresses and the radial stresses, you use as the those as the deviatoric stress and the confinement pressure on the material specimens, and conduct laboratory investigations with the material that you are going to use in the field. Okay, so identical material can be taken or used and cast specimens and test them with this stress states that are going to happen in the material, and the epsilon p, that is the permanent strain in the material due to a large number of load applications, can be determined. Now, it may not be possible to get in the field. Actually, the structure may be subjected to a large number of deviatoric stresses as well as radial stresses, so it may not be possible to find the epsilon p corresponding to all these stress levels. So, what you do is that you have a number of stress levels at which this will be tested, and then you can estimate the coefficients A, B and M. Okay. Now, once you know this A, B and M for the pavement material or for each one of these layers, then epsilon P for the vertical, the permanent strain of these layers due to the applied axial loads can be determined, and once you know this, the strain, then multiplied with the thickness of the pavement layers. So, the permanent strains multiplied with the thickness of each of these pavement layers will essentially give you the total deformation in each one of these layers. Now, if you get the permanent deformations in each one of these layers, you can add them together to get what is the total rutting on the top. So, essentially using the material parameter of epsilon p that has been determined from the laboratory, you can use it to see how the material deforms, or how the pavement structure deforms, and accumulate the sum of the total deformations on each one of these layers to get what is the total deformation on the surface. Now, what I have discussed just now is you do a repeated axial load kind of a testing on the specimen to get the epsilon p values or the epsilon p expressions, whereas there are other studies also wherein rather than using a repeated load test, you go for a creep test, that is a constant loading test, and modified shell procedure has given. This is the bituminous concrete, or you call it as asphalt concrete. Permanent deformation is given by epsilon Vp is equal to A T raised to B, whereas a similar model can be developed wherein T represents the time for which the creep test is done, okay, or the time of the creep test. A and B again are the regression constants from the creep testing. Okay, that is, so all the different pavement layers can follow the relation between epsilon p and n model that we have just discussed. Then the surface rutting of the pavement can also follow a similar trend if we have data that correlates the number of repetitions of loading and what is the rutting that is observed in the field. Okay. So, this models has been developed in terms of the rutting rate or rut depth by the number of repetitions, load applications which are developed from the field data. Okay. So, it takes a form of RR, or the rutting rate is equal to the rutting depth in inch by the number of load repetitions, which is equal to A by n raised to B, or A and B are the terms which are developed from the field calibration data. Okay. So, this is some data that has been used for the development of such models. You can see that from the ASHO road test data, that the American Association of State Highway Officials road test data, we see that the rut depth versus the number of application of the loads forms. So, this data is given for certain road test stretch, and then you can know in a log scale you can plot the rutting rate versus the number of applications. So, this is R, that's the rutting rate versus N. So, you can form a relation between them, a straight line relation can be formed. So, you see that RR is equal to 2.65 into 10 raised to minus 3 by N raised to 0.623. So, such relationships, so what you have mentioned here. So, such relationship can be directly obtained, or the such distress functions can be obtained if you have sufficient amount of field data which correlates the rutting rate and the number of load repetitions in the field. Okay. Now, what about, let me go back to the IRC design again. So, as I said, in the IRC method of design, you consider the subgrade rutting. Okay, the subgrade rutting. So, you can read from here in IRC 37, rutting within bituminous layers caused by accumulated plastic or permanent deformation in these layers due to repeated application of traffic load is another major distress occurs in the bituminous pavements. But these distresses are considered by integrating the mixed design into the structural design by incorporating the mixed volumetric parameters into the performance models and by making suitable recommendations about the choice of the binder and the mix to be used in the different layers. So, it is suggested that you can use rut resistant mixtures in the layers, and these mixed parameters can be so adjusted so as to have rut resistant mixtures, so that you may not have to consider this rutting of individual layers in the bituminous layers in the overall rutting of the pavement structure. So, this is what is recommended in the IRC code. Now, the current mechanistic empirical pavement design model. So, I will just quickly mention what is the model being used in MEPDG. So, MEPDG considers the spatial as well as the temporal variation in rutting. For bituminous layers as well as granular layers, you can see models here. Say delta P is actually the accumulated vertical deformation in the HMA layer, that layer alone is represented as this expression which has parameters such as epsilon r. So, epsilon r HMA, which is actually the elastic strain that is calculated by the structural response model. So, you do a structural analysis or the layered elastic analysis, and you can represent what is the elastic strain in that HMA. So, this is similar to what we have already discussed, that is the elastic strain is something proportional to the plastic strain, okay, and N is the number of load application, and T, the pavement temperature, is also a major factor which is incorporated in this model, and then KZ is something called the depth confinement factor, so that it will take into account the confinement pressure that is happening in the or acting on the material, and then you have you have another expression for the granular layer, which is delta P for soil, which has parameters like epsilon V, which is the average vertical elastic strain in the layer, which is again calculated by the structural response model, and epsilon R here is the resilience strain, which is imposed in the laboratory test to maintain the material, to obtain the material properties, and then H soil is the thickness of the unbound layer, and also there are constants like rho and beta in here. So you can hear rho, beta and all some of the constants. There are individual equations are given to capture all this. So I am not discussing all that in detail, but just wanted you to highlight the fact that MAPDG has given a similar approach. This the approach here, you can find out what is the accumulated vertical deformation in each one of the layers, which essentially is given as a factor proportional to the resilient or the elastic strain in the material. And then there are various calibration factors, like you have K1R, K2R, K3R and so on, which are the global field calibration factors, and there are the local or the mixture field calibration factors. So for the performance of the pavement and the performance of the mixture, you have calibration factors which can be utilized to convert this model to be used in your local conditions. Okay, so what we have discussed so far is the Rutting transfer functions. We have seen that in IRC 37, Rutting is a subgrade Rutting that is being considered, whereas there are other approaches wherein you can use the Rutting in each one of the layers, and the permanent deformations in each one of the layers can be added together to get what is the Rutting that happens on the pavement structure. So such distress equations can be again developed based on the studies that are conducted on the HMA mixtures in the laboratory and the extensive field studies that relates the number of load applications to the permanent deformations that you see in the field. Now let's move on to the third mode of failure, or the third type of distress transfer function that are normally used in many of the design approaches, though this is not used in the IRC approach. Now what is this thermal cracking or low temperature cracking? Low temperature, so it is divided into two types basically. One is the low temperature thermal cracking and the second one is a thermal fatigue cracking. Let's see what are these. See, as the pavement temperature decreases, we know that the tensile strength of the material can increase. So you can see a picture here by McLeod. So from here right to left, you see that the temperature decreases, and this graph here shows the tensile strength of the material, and the other one shows the thermal stresses that are there in the material. Okay. So we see that as the temperature increases, your strength of the material can keep on increasing, but only up to a certain level. Thereafter the strength decreases. Whereas if the temperature keep on decreasing, the thermal stresses that are coming on the structure will keep on increasing. Now a stage will reach when the thermal tensile stresses that are there on the material exceeds that of the tensile strength of the material, then in that case there will be cracking. So that is called the thermal cracking. Now the second aspect is that suppose this tensile stress that is coming on the material is less than the strength of the material, or the thermal tensile strength of the material, but still there is a possibility of cracking if this low stresses are being applied continuously for a number of time. Okay, so this will not, the pavement will not crack under the single daily application of this thermal stress due to that one temperature stress cycle, but it may crack over a period of time when large such temperature stress cycles are applied on the material. So this is called a thermal fatigue cracking. Okay. Now when I say the thermal cracking, it is a combination of this thermal cracking plus the thermal fatigue cracking. Again, there are various approaches which are used to consider thermal cracking in the design. So the one which is very common and which considered both the thermal cracking, that is the low temperature cracking, and the thermal fatigue cracking, given by Shahin and McCullough. And that chart or the sequence of steps that are to be followed to do this design procedure or to do this analysis for thermal cracking is given here in this flow chart. So I'll quickly discuss what this process is. The first of all, you have to give the input data. Okay. So input data includes weather data, the material properties, the HMA properties, and the design period. Okay. Now when I say the weather data, so any data that actually contributes to the thermal behavior of the material is needed for the for this analysis, which includes the mean annual air temperature, the annual temperature range, what is the solar radiation, what is the wind, the surface absorptivity, and all those weather data has to be input to capture the response of the or the weather how the weather changes or how the temperature changes. And the second one is the bituminous material. So again, it is a bituminous material that undergoes this thermal cracking phenomena. So in the bituminous material, you need to give all the physical properties of the material. Then the aging that happens because of the exposure to temperature conditions or environmental conditions. Then thermal conductivity, specific heat, density, the mix composition, what is the coefficient of thermal expansion of the material, what are the fatigue characteristics, and the maximum tensile strength of the material. So all these comes under the material characterization part, so which is related to the low temperature cracking. So this information has to be given as an input. Now next what we do is that you will calculate what is the hourly pavement temperature, because you have to essentially accumulate this damage and see how the damage accumulates over a period of time. So as you know that the temperature varies on a daily and as well as an hourly range, and based on this variations in temperature, the response of the material changes. Okay, so you estimate the hourly temperature at the surface of the pavement. You can use various models for that. Now, you estimate the asphalt and the HMA stiffness as a function of time. So, again from the material characterization data, you can see that at various temperatures and with aging, the material modulus and the material the material stiffness changes. So, evaluate the effect of this aging and other characteristics on the asphalt properties, and you have to determine what is the stiffness of the material over this period of time. Okay. Now, you can use various nomograms which are available. So, and also predictive regression equations are available to estimate what is HMA stiffness and so on. So, I am not going into the details of each one of this, because you can always refer to the mechanical material characterization courses to find out how the stiffnesses or stiffness or the material modulus values are estimated. Okay. Now, the next step is to compute the thermal stresses. So, once you compute the thermal stresses that comes, the extent of low temperature cracking can be evaluated by comparing what is the maximum tensile stresses with what is the tensile strength of the HMA at the corresponding temperature. Okay. Then we have to see whether there is a failure probability or not. Now, the probability of failure is given as the probability when sigma minus h is greater than 0. Now, what is this sigma? Sigma is the maximum tensile stress that is coming, and h is the tensile strength of the HMA material. So, at that particular temperature, if the stress exceeds the strength of the material, there is a possibility of failure. Okay. Now, so this is the first aspect wherein you determine the thermal cracking possibility, or the thermal cracking is being predicted based on this approach. Now, the next comes the thermal fatigue cracking approach, fatigue cracking. Now, this aspect has to be is done, since it is fatigue. This is done in a similar way as you find the fatigue cracking due to repeated loading. Okay, so here you can a similar model can be used, but it is for a low temperature. Low temperature. For low temperature, the material moduli and the material relationships can be developed, and then based on that you can predict the fatigue life, and you can use a similar approach as the Miner's approach to find what is the damage ratio. Now, for each thermal cycle, what you are trying to find out is that in the thermal cycle, how much is the damage that has occurred. Since it is one cycle, so your damage ratio becomes 1 by Ni, where capital Ni represents the total number of repetitions for the ith day for a similar pavement change in temperature. So, and N is the number of days. So, over a number of days, you can see how the damage gets accumulated, and then you can fit a normal distribution for this this Ni, that is the cumulative damages that can happen because due to the various temperature differences. Then the probability of failure is when the probability of log C is greater than 0. Now, what is C? This is the damage ratio for one thermal cycle. When log C greater than 0 means that it is always, that is C is always less than 1, that is C has not crossed 1. So then when the damage ratio is less than 1, you see that the payment is fail. Okay, it is safe. So what we have done is that in this we have computed the predicted the low temperature cracking, and you have also predicted the thermal fatigue cracking using the various approaches. Okay, now you can add these two, low temperature cracking and the thermal fatigue cracking, to estimate what is the total cracking in a specified time after construction, and see whether this is within the allowable limit or not, and whether the design is safe or not. So this is the overall approach in which you consider thermal cracking, which includes both the thermal cracking and the thermal fatigue cracking, that is the low temperature cracking and the thermal fatigue cracking, and how this is used to see whether the design, or you use it in the design procedure. This is what we have discussed now. Okay, so in the overall this session, we have considered the three distresses. One is the distress, one is the fatigue cracking, the second is rutting, and the third one is the low temperature cracking, and how the various distress transfer functions can be used, or how, what are the type of distress transfer functions is what we have discussed. Now how this will be incorporated in the design will be discussed in detail when the different design approaches are discussed in this course. Thank you.